recording at the moment. So all the videos are recorded. I'm still waiting for my mic to arrive. We've been waiting for many weeks. The mic have not come in yet. So the sound system, the system at the moment is not very impressive. Okay. So we'll try to begin our lecture and continue from where we stopped last lecture. Now, I suppose that the programming class is getting a bit more and more challenging. So as we proceed on, you would realize that the coding becomes more and more complicated. However, if you spend some time, just go through the code very carefully, try to learn from the code that I gave you. You can always able to figure out how to perform the required tasks. Okay. So the plan is to go through many different types of tasks. Then we will demonstrate how you can use Python syntax to solve these tasks. As we solve enough tasks, at the end of this course, you become sort of like half expert or expert in using Python numerical problem. People still are coming in, so I think these are the latecomers. Okay, so we have 33 here. I'll just use you an example. Okay, so let me, before I continue to burden you with all these very heavy lectures on how to write the code, let me make a small revision. Okay, so this is just the e-learning webpage. I hope that now you see on my screen. So you log into the e-Moodle, the portal, then you see many materials are given to you. So these are all the sample codes that I have written. So now, for example, we're talking about 6.2. So currently we are working on this 6.2 statistic probability distribution. Now let's look at say 6.1. Okay, 6.1 is the material that you would need to solve your assignment questions. So the assignment question that I gave you are sort of like original and authentic, right? So you try your best to solve the questions in the assignment by referring to the sample code that has been given. So you have to have very clear mind what are we doing. Okay, so you study the code, you try to understand the concept, then you try to use the syntax to solve the code step by steps. Now you will be very happy if you're really able to solve your code. Okay, so I just want to make a short revisions on the problem 6.1 because this is what you are using for. So people are coming in, have to meet people first. So in 6.1, as well as in Okay, guys, I'm sorry. Hope that you are still there, not leaving me. So internet just broke down for a moment because my pop-up has been finished. Okay, good. So let us continue. Let me check that the recording is still on. Okay, let me share my uh, so share the screen. Okay, so there's the recording. I'm sharing this. Okay, so you're still there, right? So you can see me. So let me continue. Maybe I don't know where did I stop during the disconnection of my data plan just now. So let me say what I want to tell you. So basically 6.1 and 6.0 is about generating sample data given some functions with some parameter. We try to generate some data point. Then we export the data point as some files. Then you download the files of this data point. Then you display the data point. Then you are given some information about the data point. For it's a data that has a model which is given by some formula. This formula it has some parameter. Your job is to use the function curve fit or the least square method to find. So what I am saying here is that if you look at your e-learning, I have just uploaded 2 samples. So you have seen, you see this sample Python code for fuzzy data generation, export, import data, performing curve fitting for 1 function and 2 functions. So if you click on this, okay, so you see this just a sample set of code that I just try to summarize it so that you can understand what we are doing. So this is a very useful sample code because you can use it for your assignment purpose. Actually 5 different code that is being shown here. It's just very similar to the code that I shown in part 6 and part 6.1, but I try to tidy it up, remove some of the possible error in the previous code. So first of all, in this part 1, what I'm doing here is that I define some functions in what they call a Y template. So whatever function you want, you can define it here. Then you can use this random thing to sort of like fuzzy, make the values of the function to become slightly fuzzy. After that, then you plot it and show it. So this is what is contained in the first part of this sample. Maybe I should open up my part sample so that you can see it clearer. So you can check on it. Template. This is the same as a template. Okay. This data. So this is the one that is doing the job. So the first part of this is to generate a fuzzy data. So you can run it. Then you can see that I am defining a function called, this is basically the Gaussian functions. So the Gaussian function has 2 formula. It has a parameter called sigma and mu. Okay, so mu would appear first, then only appear later. Okay, so by specifying my mu to be 1 and sigma to be 2, then I'm able to generate a sample data which is represented by this data point. Then I also show the formula of the model, the exact model, which is the continuous function. Right? So you can see that the data point that's generated is purposely sort of like shifted a little bit so that it looks slightly different from the previous one, from the original exact Gaussian function. So here what I do is I think, okay, so in this case, I just multiply the amplitude by a factor of like 0.9 something to 1 point something, so that some points are larger than the function, some points are smaller than the functions. Okay. Then this part is a function where you generate, you write out all the data into an external file. So all the X data and Y data generated in the first part of this code is then exported, right? So you're often that in your assignment, you are asked to export your data. So you open a file, you call this file name template data, then you convert all the data, X and Y data, into a string. Then you write this string to the external file at some fixed format, 8.3F, 8.3F. So this is the second part. So then this third part is that you read in the data externally. So assuming that this data has been downloaded into your hard disk, then this part of the code is to read in the data. Now this data and this data, although they are the same, but this is a function that is writing the data that is generated from the first part into an external file. This is to read in the data from, so that the data XARR that appears here would be, in principle, it's read in from the external data that has been written in this part. Okay, so this is to generate the raw data based on some formula with some fuzziness in the amplitude. Then this part is to output the files into some external data file. Then this part is to read in. When you read in, you have to make sure that you read in the first column and the Y and the next column, so that the data file that you wrote would be something like that. I think this is like so this is just so export this data and then you read also this data. And the third part of this is to perform a feed, right? So you read in the data either from the template file or from template data, or not any data that is kept in your RAM memory. Then this part is to perform the fitting, right? So you can fit the functions using optimized curve. So this sample number 4 here is just a sample that show you how you can use the SciSci optimized curve fit to fit your data. So you have to provide your function. So if you know the function is a Gaussian, then you define your function. Then you have to learn how you use the syntax. And basically, you have to define the function you want to fit with variable X. Then this is a parameter. So, so the first one is always the independent variable, and then this part is the parameters. So you want to know what is the best parameter value for mu and sigma. So you fit in the function to this curve fit. Then you also provide the data point X ARR and Y ARR is the data. Then after this result is obtained, correct, then you'll be able to obtain the best result. So the param best is this is the output, and this is the output. Okay, so what is this output? This output is actually the values of the param in the first best param. See, when you input the functions to the curve fit, is a result. The result is a array, as a 2-component array. The results with the 0th component is the values for the fat strip parameter. Result 1 would contain the error. Okay, the error in the back. And since there are 2 parameters you want to calculate, so the result 0 here actually contain 2 values. The first value is mu, and the second value is sigma. So I define my mu best to be the first element in the results 0, and sigma best to be the first element, well, the 1 element in the results 0. So that is how I extract the mu best and sigma best. Okay, mu is the sort of the 0th element in the result, and sigma is the 1. So the sequence is very important. Okay, mu refers to this mu, right? So this is a parameter that appears first. This is a parameter that appears later in the definition. So the results obtained from SciSci the first value of the result will be mu, and the second result will be sigma. That's why I define my mu to be the first one, sigma to be the one. So once the best fit parameters of mu and sigma is obtained, then you can plot it. Okay, you can plot the functions. You put this now from the solution back into the functions, then you plot it. Right? So this red color line is the function that is plotted using the best fit parameter mu and sigma that is obtained. Then you plot it and you see that yes, in this particular example, the data is nicely fitted by the function with the best fit parameter. But there are some occasions, as we have seen in the previous case, where the 5 fit or this optimized curve fit sometimes does not do a job. The parameter that is obtained, when you put it back into the formula of the model, it doesn't fit very nicely. But for this particular case, it works. And this is another example where we fit the data against an model. So in this case, it's the same model. So, but the syntax to fit the model using the least square method is slightly different from using the curve fit. So these are the code that I sort of like visualize and condense it so that you can use it whenever next time you have to fit any particular model with more than 2 parameters. So the thing is, this is something which is very weird. So the XRI is defined to be an array. So if you don't have this, somehow the least square functions does not work very well. So the syntax is that you have to define the residual in the least square method. So the residual is defined to be the difference between the data from the Y and the values of the model evaluated at the X data. Okay, so P is a set of parameters you want to optimize. In this case, there are 2 P's. The P here stands for parameters. So there are 2 parameters you want to optimize. And the first one is mu. The second one is, I think it's something wrong. Sigma, this is 1. This is not 2. Okay, so I think there's something not right here. I still got the correct number. I don't know why. But never mind, I will fix it. But anyway, this is just a sample model that you should use to do your coding. So just to let you know that I have uploaded these 2 code in the e-model in the e-learning so that you can use it for your people are coming in. So you can use this to solve your assignment. Okay, so I have already delayed the submission date by 2 days or 3 days. So you can do this. Okay, so we have spent half an hour to talk about and revise about this the previous lecture. Okay. Now, is there any questions you want to raise before we continue on the on 6.2? Questions from any one of you? So let us close this template file for a moment. And we are going to go back to this 6.2 part 6.2. Okay, so we are now working on part 6.2, which is about the statistical probability distribution. Mind you, in case you do not or you have forgotten what we have been talking about the last lecture. So in the last lecture, we are talking about different types of probability distribution function. in statistics. So there is a collections of what we call the PDF or PMF for this probability distribution. It is found in a package called SciSpy Stats. Okay, so this is what we are talking about. The main topic for this two is to talk about how we can make use of this, well, sort of a library, SciSpy library that is meant for statistics. So in this package of SciSpy Stats, you could have many different types of probability distribution function, or sometimes you call the probability distribution function as probability mass function if that probability distribution is a discrete one. So there are two types of statistical distribution: discrete one or a continuous one. I think discrete one called PMF, and the continuous one you call it PDF. Okay, so you should. So here we talk about a few types of PMF and a few types of PDF. So these are the commonly seen PMF. In this particular example, when we talk about binomial distribution, which is an example of a discrete distribution, and then we will also talk about the most important and most common continuous distribution called the Gaussian distribution, or sometimes it's called normal distribution. So the normal distribution in the SciSpy, in the Python package, SciSpy Lab has a name, right? So it's called norm. In order to call out the PDF for the normal distribution, what you need is just import the SciSpy statistics, SciSpy.stats, the library, and then the short form of this is called SS. So in order to generate the PDF from the SciSpy stats, so what you do is just that you just say ss.norm, then this will call out the normal distribution functions, and inside this norm there are many other applications. So one of the applications is to give you the PDF. If you want to call out, for example, the binomial distribution functions, you just say, okay, ss dot the name of the distribution, which is called binom. So different distribution has different names in the SciSpy.stats. Now, once you have called out the binom, then you have to decide what you want. You want to actually generate the distribution function, the PMF, for the binomial function. So these are the common thing. And the most specific is that different types of distribution function has different parameters. And sometimes this parameter is called, shape parameters. If I'm not mistaken, it's called shape parameter. So for example, for the binomial distributions, the parameters are two. There are two parameters, n and p, where the n and p have to be fulfill this criteria. The p is a continuous variable, n is a discrete variables. Whereas for say the Poisson distribution, which is a discrete distribution, it has only one parameters. So when you want to generate the PDF of a particular distribution, you have to know how many parameters are there for this distribution function, and what are the types of these parameters. Is it continuous? Is it discrete? Or is there any constraint on the values that can be taken by the parameters? Okay, so in this case, the lambda parameter for Poisson distribution happen to be just a continuous function. Okay, and this x is 1, 0, 1, 2, 3 because it is a discrete distribution. Now, x is a variable which is continuous. Therefore, we call this normal distribution. It has two sigma and mu. Okay, it has sigma and mu as its parameters. So if you want to generate the Gaussian distribution function, then this is how you get it. Okay, the Gaussian distribution function can be generated from this. Okay, so you can just this is 6.2. Okay, all nice. I'm using my 6.2 here. Larger slightly. Okay. So this is how I generate the Gaussian distribution functions. Press a button, then you got generated. So this is a Gaussian distribution function. Now, when you want to generate the Gaussian distribution function, you have to know what are the parameters to assign. So in this particular case, the parameters of PDF for this normal distribution function admits mu and sigma. But if you confuse between sigma and mu, you provide the values of sigma to mu or provide the values of mu to sigma, then you mess up things. Like then you get it wrong functions. So normally what we do is that we want to see more clearly what is the help file for the norm. Right? So you can take a look at this help file for the norm, and then this is not norm. This norm is not the norm that we are looking for. We should be looking at ss.norm, I think. Okay, so ss.norm is the correct one. So ss.norm refers to the statistical SciSpi statistical package for the normal distribution functions, and then it tells you what are the parameters to supply. Then you have to make sure that you know how to read this. I think the help file sometimes is a bit confusing. I myself do not know how to read this normal distributions help file very well. So what I do is normally I refer to SciSpi norm norm distribution function. SciSpi normal distribution function. So you have to look at the help file for this and see how you have to use it to generate the numbers you want. So I think in this case, there are some values that should refer to. You have to call out the PDF. So PDF is here. So the PDF has to have two numbers. No, it's not specified here. But anyway, I have figured out how to do it here. Now, in order to generate the distribution function, you have to specify what is the values of mu and sigma. Right? So you have to say what is your mu and what is the sigma. Now you have to know that mu is a mean for the distribution, sigma is the width. Okay, so the mu is the location where the peak locates, and sigma is the width. So in order to check that you are assigning the correct values to the first argument and second argument in the norm PDF, then you can say here, okay, for example, you said mu, if it's not 1, let's say if it's minus 9. Okay? If it's minus 9, people are coming in. So if you do like that, then you expect that this will be shifted to the left by minus 9. So let me do it. I shift this, and you see that yes, indeed, the peak is shifted to minus 9. So it means that this is correct. So this is a very simple way of generating the normal distribution functions using the SciSpi. Now, just now, right? When I show you the template file for these things, I happen to also define the Gaussian function. Right? So this is the Gaussian function that is generated using mu and sigma. So let me try to compare it with this number. So this is a part. This is a template. So this is a way how I do my template. Let's cut and paste. Just I'm just curious. Okay, I'm just curious to see this code when I combine them. I should get the file. Okay, so this is the code that is generated from the PDF of norm. So let me do it again. Do it here. This is another of sigma and mu. So I'm going to use mu is minus 9, sigma equals to 1. What I do here is I just call this mu equals to mu. sigma equals to sigma. That should be correct. Okay. So the mean is -9, sigma is equal to 1. Okay, so I just have to append my code here, and I'm generating another function. It looks like it. Somehow it's very weird. So maybe I should not do that. I just plot x data and y data, but instead of that would be just nice. Okay. No. It's getting worse. X data and y data. X data and y data that I obtained from here, it doesn't look like it. Okay, so data that is obtained from here. Here, this one seems okay. This is from 0 to 0.4, where this one that should be correct. It should be exactly the same. But for some reasons, I don't get it run correctly. Let me restart and clear the output. Just try it again. Okay, so what I'm doing is that I have two different independent ways of generating the data. First, I have this way of plotting the graph, and then I also have another way of plotting the graph. Sigma naught. So this should give me a function. Then this would also give me another function, and both should be the same. So maybe this is not right. So this is not defined. Maybe I should define it here. That's all. To transport one file from one program from one file to another. Since we already done it as well, we finished doing it. Okay. We put the file lab here so that yeah, it doesn't look like it. Data, one data. Yeah, so it's generated from here doesn't seem to be white related. Maybe should be white template. Maybe I think let me try again. White template. White template. Okay. Now maybe okay. So what I'm trying to show you is that you can generate the norm functions from here, and you can also generate the functions from this as well. Oh man, it shouldn't be like that. It should be able to do it. Maybe I should just try it again. Data and write template. T column should be mu and sigma for T in X data. It should work. There's no reason why it should not work. Data is this 50 X new X plus. Okay. I don't know why it doesn't give me the correct number. Okay. So no, maybe I should not waste time here trying to prove something which is not that essential. Okay. Now let's continue anyway. So you should now at this moment learn how to use the statistic package in SciSpi to plot the PDF for the normal distribution function. Then you can also use here. This is another example where you can also plot the binomial distribution function by just calling this SS binom, and then you just apply the values of n and p. Okay, so you can specify the n to be 9 and p equals to 0.1. This is the parameter that specify the binomial distributions. You press the button, then you call it out, and then you plot it. Okay, so this is what we have been doing since in the last lecture. Okay, so also I explained to you the idea of doing the beginning, right? So if you have a set of sample, then you want to know what sort of distribution of that set of sample is. Okay. So in this example, you can get the sample data set. So this is a sample data set that is generated. So what we do here in the lecture is that in the previous case, we use this part of code to generate a data, right? To generate a set of data that is that has this distribution. So here we generate the data based on let me see. It's not like that. Space long. This is not the generation of the data. Sample data. Okay, so let me explain a little bit what is being done here. So we use the RVS. Okay, so RVS is a function that is found in ss.norm, right? So ss.norm in the previous example has been used to generate the PDF, right? So if you say ss.norm.pdf with the values of mu and sigma defined, then it generates the PDF. But if you use RVS, which stands for random variables or random variates, then this function would be able to generate for you a set of data points, a set of data where the distribution is distributed according to the normal distribution with the specified parameter sigma and mu. So here we set the sigma to be 6.4, that is the width of the normal distribution, and we just simply set the average of mu for this distribution is minus 0.37. So this would generate the data. So how would the data looks like? Now the data is a set of number. So this is not, I think the data is a sample data. The sample data, which is generated from the RVS, is this, right? So it is a set of number. How many number are there? The number depend on how many you want it. So there's a column inside RVS, the third column, that you can specify the numbers of data point you want. So here we generate 500 data point. So you can count this, and then you can ask what is the dimension? Dimension, no, sorry, it's not dimension, it's the length. It's the length of this array. So it says that the size of this sample data is 500. That means that's 500 data. So each of these data are generated from the normal distribution. So there are so many distributions. So what we do is that you want to sort it out into bin. So you use this method that I mentioned here. So you sort out the largest values of the data point and the smallest one. So the largest one will be placed here, the smallest one will be placed on the left. Then you decide how many bins you want to divide this data. Say 20. Then you count how many values of the data that lies in the first bin, etc. After you have counted the numbers of data in a particular bin, then you divide the numbers of data point in that bin divided by the total numbers of data point. then what you got here would be a probability. That means if you close your eye and simply take out one number from this data set, then the chance that this data set fall in a particular bin is proportional, is just given by the probability, that is the values of the y-axis here. So this is the idea of the histogram. Okay, so you can do, so you can generate this data point very easily. Once you have generated a data point, then it is possible to bin this sample. Right? So what you do is that you just put this sample data into a histo. Okay, so what you need is this. Let me try to see how I construct this. Let's do this. So there's a function in the PLT. Now, is the matplotlib. Okay, so it's defined here. PLT is a function which is the pyplot in matplotlib. So we are going to use this matplotlib pyplot very often from this day onwards. Okay, so inside this pyplot function, it has a function called histo. So inside this histo, if you put in the sample data, so if you put in the sample data, which is just a set of 500 number, then you have to specify how many numbers of beans. Okay, so you say 20 beans. Okay. 20, if I'm not mistaken. And then you will say density equals to true. Okay. I forgot. I think this is one. So you say beans equals to 20. Then you say density equals to true. Then you'll be able to bin the sample into a histogram. For some reasons, has no attribute history. Yeah. So so this is a histogram. So if you recall earlier on in your tutorials or in exercise, one of your assignments in the early days, before the lockdown, you are asked to also write a code to perform a histogram. Okay, so this is a histogram that is obtained from the sample. So the sample can be easily generated from RVS. Okay, so this whole process allows you to learn a very simple trick. Next time, very often in the physics learning or in experiment, sometimes you need to generate many different mock data. Right? So the data sometimes has to be generated computationally. You need this data to say to model something. And you need the data to be having some kind of specified distribution, with Gaussian distribution or sometimes student distribution or whatever distribution. So you can use this method, okay, ss dot whatever distribution dot RVS, then it will be able to you will be able to generate this data set for you. Now, once you have generated this data set, you want to see with your own eye that indeed the data set is generated, indeed has the right distributions that you are looking for, right? So if you generate more data set, or if you generate more data point, then the bin will become more and more close to the theoretical one. So this blue color bar represent the numbers of the data bin. And these numbers should sit on the formula of distribution function that is describing this distribution. So since we are generating the normal distribution data set, then if you plot the functions of this data, of this histogram, okay, so this is the normal distribution function we have just plotted. So this function, when you plot it, it looks like this. Okay. So if you then when you plot here, the beans that is this would give you the histogram, and this PLT plot will plot the values of the beans at the edge. So this is just a point, okay? So here we are plotting the histogram, and this his is the height of the probability, whereas the beans is the values of the beans. So maybe let me show you what I mean exactly by this. So you can count this one. This is the results. This is a numerical result that describe the histogram. So PLT HIST is, according to the definition, obtained like applying the histogram function to the sample. And the result of this whole thing is this, right? So you have one array and two array, and then you have the third thing. This is just, I think, if I'm not mistaken, it's just some extra information that is used for plotting the histogram. But what is important here is that this is the histogram value, which is the probability, whereas here this one is the values of the beans. Now remember, the beans is having a width, right? So a width would have hand border and right hand border. So this refers to the first value of the the left hand values of the x in the bar. So if you count this bean, it has one more number than the height. So we call this to be the beans value. This we call it to be the histogram. So this is what I'm doing here. So I call, So I call the first component in the PLT HIST, and the next component or the middle component in the array of PLT HIST to be the beans. Okay, so the beans is just this array, whereas the histogram, the HIST is just this array. So let me say this beans is just this array, and then HIST is another array. Well, maybe I call this HIST. HIST is just a name. Okay, I think it should be called this PLT, the zero component. So this is the height of this. So you can actually then plot both together. You can plot the beans, and you can plot this together. Can you? No, you can't. Can you? No. Yes. No. Yes. No. Let's see. Maybe yes. Maybe no. No, you can't. If you plot it, you wouldn't got anything. Right? If you plot it, you wouldn't get anything. The reason is because the beans has one more element, has one element larger than the height. Okay, so for example, if you see the beans start from here, this is the first value. So for the beans, so you have 1, 2, 3, 4, and then you count as these extra numbers in the beans compared to the numbers of the height. Okay, so if you want to plot this point, what you need is this. So beans is just the values. Then I define what P is. So P is just a norm, right? So P is generated to be the numbers that you put into the PDF. So you tell the code. People, so let me explain. See, my purpose is whenever I write a code, I just want to make sure that you understand what I'm doing and how it's done. I hope that by doing this demonstration, you understand this better. Okay, beans is a set of numbers. So what I want is I want to plot the values of the PDF for each values of the X in the beans. Okay, so how do you do that? It's very easy. So you define your P. So this would means the values of the beans that should goes in. Okay? So if you do like that, let's see what you get. Let me see. Then you say print P. So here you get a set of number where the values of P is evaluated for each values of beans, and there are many values of beans. Right? So that then you can easily plot the values of beans versus P. Then you it looks like this. Why is that beans is not? Well, let me say it again. Beans. So the beans should start from minus 21 up to 23. So when I the beans, I plot the P, and I got this number. So when I PLT a plot of beans versus P, I expect the plot to be starting from minus 20 as well. So that is how I got this. Okay, this is just a plot that is obtained by evaluating the values of the PDF of the normal distribution function at each values of the H in the beans. So this would give me a plot. The histogram would also give me a plot. So if you don't say anything, then this together with the plot will be shown on the output. And this is just overlap of the two outputs. So you can see very nicely that the values of PDF is generated from the curve and from the sample, they are sort of like agreed, right? So ideally, the values of this should be like here. The point should be the values of the P for at this age should be somehow agree with the height of the bar, right? But you don't need to be exact. That is because the agreement between the histogram and the formula for the PDF depends very much on the numbers of sample and also depend very much on the beans. So you can increase the numbers of sample and maybe you can increase the numbers of beans and see whether you get a better. Now you see a better agreement. Okay, so let me move on to the next part. So here I just want to show you that you can generate high quality statistical data sample based on your requirement. After you have generated the sample, you want to verify it. So what I'm doing here is to verify for you that yes, you plot the beans, the histogram of the sample, then you overlap it onto the theoretical PDF of this distribution, and you see with your own eye that yes, the data that is generated indeed agree with. That is what I'm trying to tell you. So here is another example. So what we do here is that we generate the histogram or generate the sample data for the, maybe I cut and paste and do it into two parts. Let me cut this, then so this part is just to generate the 50,000. There's a lot of data point I do. Then I ask the computer to use SciSpy statistics, generate the random variable for the binomial distribution with the parameter n equals to 20 and with the p parameters equals to 0.5. And then I want the size, which is numbers of the point to be 500,000. After that, after you have generated the sample, show me the histogram. Okay? So that is how I do it. So this is a histogram of the sample. Right? So you can try to make the sample histogram to be finer, say 50. And this is the histogram. It doesn't look very nice. I think for some reason, for some of the beans, the data is just zero. So usually what you want is that you want to generate a sample where it is mostly non-zero in a particular bean. So maybe you reach 30. then there's something missing, so it's kind of annoying. Okay, so it looks better now because there's no bins and the probability is falling to 0. So if you make it to be, say, 30, and yet find some bins where the probability is 0, then we want to do it again. So you want to generate a sample that is good enough where there's, okay, so the way how you do it is that you just make the bin number to be slightly small. So that the other way is to make the number to be larger, maybe 70. So I think the way how we do it is just to make the numbers of bin to be less than no. So we stick at 20. So that's how you generate this data. After you have generated the data, you plot the bins. This is the bins, and then here I am generating the theoretical curve for the binomial distribution function. So this is the function that is for the binomial. Then I plot it. Okay. No, it doesn't look like it. For some reason, it's no. This is bad. For some reason, it histogram, the p histogram n and p. No, maybe the n is just too large. Maybe n should not be. Maybe n will be just fine. Let me set the n to be 10 instead of 20. Okay, so now it's better. So for some reason, if you n to be too large, then it doesn't work very well. So now if I set n to 10, then you can show that this is the theoretical values for the distribution of the binomial with parameter n equals to 10, p equals to 5. So after you have done that, then you want to combine both together. So you can combine both data, both, and you see. So the height of the data, height of the bar is the one that is generated, collected from the sample, whereas this dot is the one that's predicted from theory. Right? So this is the one that is predicted from theory. So you again feel assured that the sample that you generated indeed do fulfill the normal distribution, these are binomial distribution, and the distributions will agree with the theory. So after that, then you generate the data and you fit the data according to the theory. Okay, so before we take a break, I just want to mention this very simple descriptive statistics for a set of data. Right? So in this example, we have a set of data. Then what you want is that tell me what is the average values of the data. Maybe let me sample data. Okay. So if you type sample data, so this is a set of sample data which are all discrete numbers, which is following the binomial distribution. Now, if you generate this, the Gaussian distribution function, then the data will be continuous functions. So it's a huge numbers of data set which have don't know how many data points, 500 or 5,000. So now you ask the next questions. You ask some statistical descriptions of this sample of data set. There are 5,000 numbers there. Tell me what is the average of these 5,000 numbers. Right? So this is the first thing more people will do. Then people actually want to know a few more quantity other than the statistics. Okay, so a few important statistical number that is needed in order to describe a set of data. Okay, so we will be talking about this maybe after taking the break. It's 4:09. Maybe we take a break of 5 minutes. Come back at 4:15, then we'll continue. Okay, so maybe at 4:16 I'll begin the lecture again. So we'll take a break of 5 minutes. Any questions? You can always ask me to the chat, or you just raise your hand, or just say something on the screen. Okay, so we take a break now. Anytime, anything? Anything? No question? Okay, everyone, welcome back. So resume our lecture for this afternoon. Yes, of you staying back. A few more people has gone missing. Okay. I'll continue my teaching. The next thing I want to spend a few minutes to talk about statistical data sample. Now, this is a very important aspect when you do science, right? So when you do science, you do a lot of data collections. So, for example, your experiments in the lab, you measure many sample data. You have to perform some kind of analysis on it. The most common example is say you measure the object falling at some height, right? So you repeat your experiment many times. You put the object at different height, then you measure how long it takes to fall through some distance, right? So maybe you put the object at a meter, and you count how many you record the numbers of seconds it falls through 1 meter. You repeat it 10 times. Then you put it at 1.1 meter, then you let it fall, then you measure the time again for 10 times. So you change the height from 1 meter, 1.1, 1.2, up to say 5 meter. So collecting all this data, then you would want to know what is the values of the gravitational constant, things like that. So usually this set of data, you want to know two very important quantity from it. Now, when you have a set of number, it's not only the number that is important, it is also the spread of the number. So I'm talking about here the spread of the number. Say you have now if you have say 5,000 data set, right? So a set of 5,000, 50,000 data point, then these are all the individual number, right? So you don't want to know actually all the individual number. What you want to know is sort of like the some numbers that somehow would provide you some significant informations of all these data. So the most common thing to realize is the average. Okay, so the average of the data can be calculated through a very simple formula everyone learns since you are in the secondary school. So for a set of xi, you can calculate the mean very easily. Like just sum up all the. I think there's an error here. So this is an error that I have to correct. The bar, which is the mean of the sample, should be just 1 over n b, where b is the numbers of 1 over n. So there's a error that have to be corrected. So this is the mean of the sample. So you sum up all the data value divided by numbers of data. That will give you a mean. But knowing the mean is normally not enough. How the data spread. So the very simple way to describe how the data spread is asking what is the width. Right? So you plot the histogram of the data, you can all do that. Then the width, right, the width of this data somehow will give you the spread. The spread is now if the histogram is symmetrical, then usually the highest peak is taken to be, well, in this, okay. So the mean is the location of X where the probability is the highest. Okay, so so the width somewhere between the lowest and the peak, you take the half of it, then the width is a very simple way to measure the spread of the data, and we call this spread sigma. Okay, sigma is roughly the width of histogram. It gives you how large is the spread. So for example, if you say you measured say 100 numbers, and each numbers is say the radius of a pencil. So you have, say you work in a factory, you have 100 pencil, right? So then you measure all these pencils. Each of these pencil give you a values of diameter which is almost the same. So in that particular example, if you plot the histogram, then you find that your histogram will be very, very sharp, right? So, and the width is almost zero. Right? It means that most of the diameter of the pencil is centered around the average value. And if the spread is very, very tiny, it means that the error, well, I'm going to say the error, the spread in the data is very tiny. Now, if you, but in most of these real life situations, the data does not follow a very sharp, very narrow distributions. So you have various values of data that you will measure. Then the spread is. Okay, so we define the spread of sigma through what we call a variance. So you define a quantity called variance. The variance will contain information of how large the data point spread above the average. So is the variance. So these are the formula that most of you should be very familiar with, right? Especially in your first year lab and second year lab. So you measure the variance very easily. You always do that. So you sum up the discrepancy between the individual data point xi and the average. Then you take the square of them and you sum it up divided by n minus 1. So that will give you the values of the variance. Now, if the n number of data point is very large, whether you divide it by n minus 1 or divide it by n, then it doesn't make much difference. Okay. So this is called the variance. Then you define what you call the standard deviations of the sample. Now the sample, so see the variance here and the standard deviations are related. So S is the square root of S. So S is the so-called the standard deviation of the sample, whereas variance is the variance of the sample. So you very careful about the way how you name it, okay? The variance of a sample as well as the standard standard deviations of the sample, both is defined by referring to the whole sample. Okay, it's defined with respect to the whole. So we talk about the distribution or the spread of the sample, which is variance. Variance is the S squared. So if you talk about only S, then the S is the spread. Well, S is about the width of this. Well, S squared is the way how you calculate the variance. So what you do is you calculate the variance first, then only you derive the deviation. Okay, the standard deviation of the sample. So then there's this quantity, which is sometimes it's a bit confusing. Okay, be very careful about this. So when you have a data, you calculate the mean. From the mean, you calculate the variance of the sample, which measure the spread of the sample as a whole. Then you calculate the standard deviations. So the standard deviation is just the square root of variance. It's also a quantity that describes the spread of. But there's one quantity which is something what we call a standard error. Okay. Now standard error is something which is different. Is not referring to the distributions of the sample as a whole. The standard error is referring to the error in the mean. Okay, so there are the mean of just the mean of the sample. Then the variance of the sample is about the spread of the. If you ask what is the error in the mean, okay, this different than saying the spread of the sample. So the spread of sample is the spread of the sample. The error in the mean is the different questions. Okay, so the standard in the means is defined to be the standard deviation divided by the square root of n. So this standard error is the number that you would write down in your experimental lab book as the error in the values of the mean. Okay, for example, if you take say the length of say you are given some 100 different types of ropes, some long one, some shorter one, but more or less all of these ropes are almost equal length. So you measure 100 of them. Some length is like 100 centimeter, the other one is 99.9 centimeter, the other one is 102.2 cm. So you measure all of this. Then you would report the average length of these 100 ropes. What you measure is, now you measure 100 of these ropes, then you calculate the mean of the based on this very simple formula. Once you have done that, then you also have to report in the length of the rope. So you are actually not reporting the error in the length of the rope, but you are reporting the error in you are reporting the standard error in the mean of the rope. Right? Remember, in your lab, you always report the mean and also the error in the mean. The error in the mean is what we call standard error. It always goes together with the mean. So when you calculate the mean, you also have to report that the mean as an error, which is given by sigma x bar. All right, so it is this formula. So what I want to tell you is the difference between the standard deviation and the standard error. These are two different things. When you report the error in the mean, you are reporting sigma x bar, reporting the standard deviation. Okay? So given an example, you always calculate the mean and then you calculate the standard error. Okay? So very simple. In this Python, you can calculate the norm very easily. So you calculate these four quantities very easily. Example, I do here, I generate a new set of sample data. So here I generate a sample data, 500 of them, And these data are generated using the RVS function for a distribution which has a mean norm minus 0.75 and have a sigma of 6.4. Okay, this is just two parameters that I set. Then I generate it, then I plot it. Maybe this is not large enough. Maybe I should make this not larger, maybe 5,000. The 5,000 because I see there's some imperfection here. So by increasing the numbers of data point, then the distributions of the mean should actually be much better. Okay, so this is the distribution of my data. Simple question: what is the standard deviations of this sample data? So the sample data is sample data. There are many sample data. 5,000 of them. Yeah, 5,000. Yeah, 5,000 of these sample data. The mean is calculated. Mean can be calculated by using this code, which you can read very easily. The mean, where is it? Okay, the mean is calculated using this SS dot mean. Okay. SS you do is that you just say size by mean. The size by mean sample data would allow you to calculate the average of these data. 5,000 numbers. The mean can be simply obtained by say size by dot mean sample. Okay. Then you can also calculate the standard STD. So the STD here stands for the standard. Yeah. Okay. So this STD stands for the standard deviation. Okay. Standard deviations STD. So the standard deviation is the definition for this. Okay, standard deviation is the square of mean of variance. So the variance is this, and the standard error of the mean. Okay, the standard of the error of the mean calculated by saying SS dot SEM sample data, where this SS is the science stats. You can look at this. The mean is contained in size pi. The standard error, the standard deviation is also contained in the size pi package. But if you want to calculate the standard error of the mean, I think SciSpy does not have the function for you to calculate the standard error of the mean. You have to use the SciSpy statistics. Only then you are able to calculate the standard error of the means. And the variance of the sample can be easily calculated using this. So these are just a very simple keyword that you could use to calculate the means, the variance, standard error, and standard deviations of the sample data. Okay. Now, since I generate the sample using a normal distribution which has a mean of minus 0.75 and it has a sigma which is sort of like this. So the sigma here more or less is the same as the standard deviation. Okay, so the standard deviations here, sigma, for the norm should roughly with the sigma, whereas the mean of the sample data should roughly agree with the values of mu for the normal distribution. Okay, so let me try to check again the values of the means. So the values of the means is this. And what it is? It is minus 0.65. When I generate as minus 0.75. So it looks pretty close to each other, not exactly close, but quite close. So the mean I want to show you is the values which could be compared to the values of mu that is used to generate this data. Whereas the standard deviations, STD, that you calculate from this sample, which is a formula, which is the square root of the variance. calculated to be 6.49, and this should be agreeable, or should agree with the values of sigma, which roughly measure the spread of the wave. So what I'm showing you here is actually two steps, two things which are two different things. I generate a set of data using normal distribution with mu and sigma separately specified by me. After the data has been generated, I bin it. Right? I don't really need to bin it. I can use the definitions of the variance, standard deviation, and means to calculate this quantity from the sample that is generated from the RES. It turns out that yes, the mean and the standard deviations for the sample data indeed more or less agree with the mu and sigma that is used to generate them. So, well, in this case, the agreement is not that excellent. So, for example, the mean is this, but the mu I got is -4. Let me try it again. Well, I tried again. I keep on trying, but sometimes the mean could be larger or could be smaller, but it won't be too much. Okay, so to check that indeed the mean and the standard deviation is always very similar to the expected one, but the means is not always. Okay, so you can try to change this. For example, the sigma, you make it to be, say, the sigma cannot be negative. Okay, sigma has to be positive. Say the sigma is, say, 0.95, for example, 0.5, for example. The mu, let me make it to be, say, 7.5. We can make it larger to be smaller, it doesn't matter. So let me try it again. So you see now the agreement seems to be better. The mean should be much closer to the theoretical one, and the standard deviation is also much better. Okay, so maybe try again. Mu to be, say, -7.5. Instead of using 5,000, let me use 500,000. And you see that yes, the standard deviations means now seems to agree much better with the theoretical one. Okay, so after this lecture, you learn a little bit of the tricks, how to use Python to treat statistical data. You can generate statistical data as you like. Also confirm that the sample fulfills the distribution you generate from, and then you check it. Okay, then you calculate the means and the sigma. Now the mu and sigma in this case can only compare to the mean and the standard deviations if the sample is distributed according to the normal distribution. If you have a different distribution, whether the mean, sigma, whatever, it would not in general be comparable. So for example, there's no sigma, there's no mean in your binomial. There's only n and p, right? So in your binomial distribution, there's no definition for the sigma and mu in their parameters. So in that particular case, there's no predictions, well, maybe not clear-cut predictions where you can compare with when you use this distribution data. But for normal distribution, the theoretical mean and the theoretical standard deviation can always be compared with the theoretical sample. So I think in your assignment, I think you have an assignment here. The assignment is, let me check the assignment. I'll get you to do the written attendance later. Look at the assignment. I think one of the assignment is to, time to look at your assignment. 6 point, we have prepared this assignment, part assignment 6.2. Assignment 6.2 is similar to what we have done. So what I do here is that for this assignment, so in this assignment, we are asking some questions not from the distribution, but we look at the chi-distribution. It's very simple. I want you to know, to show me that indeed you know how to generate the distribution functions for the chi-square distributions. So chi-square distribution is defined is defined somewhere here, chi-square distribution. There are many distributions. One of the distribution is a chi-square distributions. So this is the chi-square distribution that looks like this. Okay, so this is the chi-square distribution formula, which is defined based on the gamma function. Right, so it has a shape parameters which is described by positive integer. So this chi-square distribution is asking you to plot the distribution function from 0 to 8 in the x value for a different chi. Okay, know how to do it for yourself. After that, you're asked to generate the data, right? So you fix mu equals to 3, which is the, I think sometimes it's called mu, not chi. Okay, the chi-square. Let me check the chi-square distribution. Chi-square distribution here, I use a k. Use a k, whereas in the assignment here, the assignment here we are not using k. We are using a mu instead of k. Okay, but it's the same thing now. Okay, so the mu here is a k. There is the same. Okay, so you are asked to use the RVS function in the scipy.stats to generate to generate 1000 data, and then do the binning, bin the data, and then overlap the data, the functions of this chi-square distribution, and you have to show me that the data that you generate from RVS indeed form a bin or histogram that could be directly compared to the theoretical formula for this. So this green color continuous function is this functions for chi equals to 3. Okay, so just show me this. So this is basically an exercise that is very similar to the one that we have done in the previous in this case. So this is just what I have done. To plot this function, to overlap the function onto the PDF of the Gaussian distribution to show that both agree. It says that in your assignment here, you are not showing this agreement for the distribution function. For the chi-square distribution. So if you know how to do the comparison between the bin data and the theoretical distribution function for Gaussian, then you should be able to do this for the chi-square distribution function. Okay, it's a test of understanding. Then I also give you another challenge. So I generate a data. Okay, I generate some data which are generated, and then you can download this from this data set. And you're told that this data set has this distribution. So you just carry out this line. So read in the data, calculate the means and sample, whatever. So just calculate this from the sample data, which is very simple and straightforward using the keyword that I showed you just now. Then you're asked to perform a binning. Now you just cast the data that you read from here and then plot it into histogram. Then the histogram should now have the age which is shown. Then you just follow this line. So you are asked to use a SciSpy optimize. This is something, this is error here. Anyway, find out what are the values of sigma and mu square that I use to generate the data. Right? It's a guessing work. I generated the data. I do not know what is the values of sigma and mu. So you have to figure out how to find out these values of data. Now, once you have calculated the best fit parameter of mu and sigma, then you can plot the function of the Gaussian distribution function using sigma and mu, and overlap onto the bins to show that yes, they do. So this is the exercise for you to do. It's not that difficult, but I think it's doable using all the documents that I have provided you. I think it's raining. It could be very noisy from my house. So let's see if you want to continue. Any questions? So that ends our part 6.2, and we are going to. We have a test. Yes, we have test sooner or later. I have to figure out maybe next week. If I have a test, we will have it on next week. Okay, next week. Friday. So maybe let's just try to tentatively fix the test next week Friday. I have to figure out how to carry out the test for you about the test project. So most likely we have it on next Friday. The test will be lasting for 1 hour. It should be quite short. Okay, so it will not be very difficult. But I have to think of how to do it online for you. Okay. Now I will have to continue with the next topic, part 7. Now part 7 could be more challenging. Part 7, you can download this. Now this is the attendance. You cannot take the attendance, but I'll let you take the attendance later. Now part 7 is about integrations. Integrations you can create out numerically. So I think this is quite advanced. So I need to talk about the integrations in detail. We are going to talk about how you perform one-dimensional integration, two-dimensional integration, and also how to visualize a two-dimensional integration. So this is one-dimensional integration, right? So you have a functions. So well, maybe like this. If you have a functions that looks like this, just integrate the function. So the integration of function can be easily done if it's 1D. But there are sometimes more complicated functions where the each function is indexed. So we are going to go through this again. After that, we also have to learn how to plot a function which has two-dimensional argument like this. Right? So the two-dimensional argument could be a two-dimensional integration could be slightly more complicated. So maybe this is not a good time to continue. I think because it's getting very noisy in my house. Okay, so so you have to submit the assignment. I'm going to make the assignment 6.2. Assignment 6.2 have to be submitted maybe within a week. I give you 7 days to do it. Now, any questions before I end my lecture for this afternoon? So there will be some slight corrections to the notes and also to the assignment questions. Every time when I find errors in this assignment or in the lecture, I will correct and update. So you will see that the versions on the web page will be keep on changing from time to time. Okay, I just want to make sure that any error that is found there will be corrected. So before we do next week, we stop at part 7. Integration will be done next week. So if there's a test on next week, I will make sure that I'll give you questions that you can do. Okay, so you would not be asked very, very difficult. Okay, so to make life easy for everyone, try to go through all the exercises that we have seen, that we have learned from part 1 up to part 6.2. That is taught by Dr. Saiko would not be tested now, okay, because I think his assignment is a bit difficult. But I expect that all the assignment that you have done, except Dr. Saiko's assignment in particular, and also all the exercises, I will ask you questions based on all the knowledge that I have already taught. Then you have to use this knowledge to do some simple tasks for you. Okay. So maybe we'll just stop here for a moment. I'll see you next week. Okay, so make sure that you attend the assignment yourself. Don't copy. You can always copy, but it's actually bad for you. Okay, so try to learn. You have enough sufficient information that is provided to you. So take it as an exercise to do assignment and stuff. Any questions, you can always ask me later. Okay. So if there's no question, then we on. Yeah. And I'll see you next week. So take care of yourself at home. Okay. So that's all. And yeah.